In this video, we will explain one of the most important continuous random variable, which is called the normal random variable. This random variable depends on two parameters, sigma, which is any positive number, and mu, which is any real number. One thing is that since this is a density function, then we must have that the integral from negative infinity to infinity of f of x dx must be 1. The graph of this function, if this is mu, the graph of this function looks like this. It's symmetric with respect to this line, and it has the x-axis as an asymptote, and this integral says that this area is equal to 1. Using Calc 3, we can prove this. Let's see, we want to show that the integral of 1 over a square root of 2 pi sigma e to the negative 1/2 x minus mu over sigma squared dx is equal 1, but then let's call this I. And then we have that, let's do the following change of variables. C equal x minus mu over sigma. Here the limits are negative infinity to infinity. Then dc is just 1 over sigma dx. And then this integral, clearly, if x is equal negative infinity, c is also negative infinity, and if x is infinity, c is also equal infinity, then this is negative infinity to infinity, and 1 over a square root of 2 pi. This sigma dx becomes dc, and we have e to the negative 1/2 c squared dc. Remember that we are calling this number I. We notice that I is also integral from infinity to infinity of 1 over a square root of 2 pi e to the negative 1/2 w squared dw. Then if we multiply I times I, which is I squared, this is just 1 over 2 pi. These two constants comes out, and when you multiply you get 1 over 2 pi. The integral from negative infinity to infinity of e to the negative 1/2 c squared dc, and here the integral from negative infinity to infinity of e to the negative 1/2 w squared dw. But since this integrand is independent of c, then we can just say that this is 1 over 2 pi, the integral from negative infinity to infinity, the integral from negative infinity to infinity of e to the negative 1/2. And when we multiply these two functions, we can add the exponents. We get c squared plus w squared dc dw. But then we can think about the plane CW, and we can think about the change of coordinates. C equal r cosine of theta, W equal r sine of theta. And doing this change of coordinates, we compute the Jacobian. We get that dc dw is just r times dr d theta, and then this integral becomes 1 over 2 pi, the integral from 0 to 2 pi. Theta will go from 0 to 2 pi, and r will go to 0 to infinity, so that we cover the whole plane. And this is the integral from 0 to infinity of e to the negative 1/2 r squared, and this becomes r dr d theta. Since this is independent with respect to theta, then we can do the integral, and this integral will just cancel out the 2 pi, and we will get that this is the integral from 0 to infinity of e to the negative r squared. And this integral, using substitution, is just negative e to the negative 1/2 of r squared from 0 to infinity. Notice that when you do the derivative, you get the negative 1/2 comes down and it cancels the negative, but then the inner derivative is a 2r, and that gives us the 1/2 and the 2 cancel out, and that gives us this r. And clearly this is when you evaluate at infinity, you are computing a limit, and when r is very big, since it's multiplied by a negative number, by a negative 1/2, this number becomes very small, becomes 0. And when you evaluate at 0, you get minus negative 1, which is 1 as expected. Then I squared is 1. We know that I is positive, and therefore this number is 1. That means that indeed this area is 1. That is one of the properties that we want from a density function. Let's compute the probability of this random variable to be between a and b. Let's suppose that this random variable is denoted by capital X. Then the probability that X is between a and b, by definition, is just the integral from a to b of 1 over a square root of 2 pi sigma e to the negative 1/2 x minus mu over sigma square dx. But if we do the same change of coordinates that we did before, if we do c equal to x minus mu over sigma, then these limits become, when you replace x by a, you get a minus mu over sigma, and when you replace x by b, you get b minus mu over sigma. And here dc is just dx over sigma. As before, this is dx over sigma. That means that this part becomes dc, and then you get 1 over a square root of 2 pi e to the negative 1/2 c squared dc. And here is the main observation. Notice that this x depends on a parameter mu and sigma. But what happens if we have sigma equal 1 and mu equals 0, then we get one particular normal random variable, which is called the standard normal random variable. And that is given by this formula, 1 over square root of 2 pi and e to the negative 1/2 c squared, right? This is the formula, and we're going to be calling this the random variable capital C. For the standard, that means when sigma is 1 and mu is 0. But then when we think about this is just the integral of this density function. That means that this is the probability that the standard normal random variable is between a minus mu over sigma and b minus mu over sigma. And that is just this integral. Something that is interesting is that even though we were able to compute that the integral from negative infinity to infinity of this function is equal to 1, to compute explicitly this integral is we can say that it's impossible. And then we have to rely on some table. This is the table that will help us compute the probability of normal random variables. Let me say that the graph of this function is like this. It's an even function. It goes like this, and it goes like that. And we know that the area under the graph is equal to 1. But then we would like to have a formula for the cumulative function. Cumulative distribution, which is the integral from negative infinity up to some value, let's say little c. Then is this integral from here to here. One observation is that this function, let's call it c, it has the property that if you want to compute c of c, let's suppose that c is bigger than 0. Then if you want to compute this area from negative infinity up to this value, then we can compare this area with the area of c of negative c. Negative c is here. The area from negative infinity up to here, this area, we can see that it's equal to this area here, right? It's equal, this area is equal to this area. And what is this area? This area is just the whole area, which is 1, minus the area before that. Then this is a formula that we're going to be using. And why this is important, since this integral is impossible to do, we have to rely on some table. And then the fact that there is a connection for the cumulative function when c is bigger than 0, and between the cumulative function evaluated as c and the cumulative function evaluated at negative c, this is the connection. When c is negative, or when c is positive, then negative c is negative. If you want to evaluate a cumulative function at a negative number, it's just 1 minus the cumulative function at the opposite, which is positive. That means that we need just that table for values of c that are bigger than 0. The next property is that we have this property. The next property, let me redo this picture. When we have 3.49, this area, we have that this area is 0.9998. The highlighted number at the bottom right shows the cumulative function at 3.49. That means that this area after that is very, very small. And therefore, if we are approximating up to 3 significant digits, we can assume that everything interesting happens between 3.94 to 3.94. This whole area is almost 1 if we're approximating with 3 significant digits, and then we can any other area that is smaller than this or bigger than that, we can round it up to 0. Then this is the formula, an important formula that will allow us to compute the probability of the normal variable for any parameter sigma and mu. Something interesting also is that the reason this parameter is called sigma and this parameter is called mu is because if we compute the expected value of this random variable, which is just the integral from negative infinity to infinity of 1 over a square root of 2 pi sigma e to the negative 1/2 x minus mu over sigma square, and then times x times dx. If we compute this, we can check that this is just mu. Then the reason of this name is because if you compute the expected value of this density function, you get mu, and also if you compute the variance of x, you can check when you do the integral, you can check that this is sigma squared. That means that sigma is indeed the standard deviation of x. Let me organize this information a little better. That means that if we have a random variable with parameters mu and sigma, and we want to compute the probability that x is between a and b, then something that we can do is we can just subtract mu in both parts, and we get this. And then we can divide by sigma. And then we can call this the standard random variable. And then this is our C. This random variable has mean, or it has a expected value equal to 0 and a standard deviation equal to 1. Then this is the one that we can get from the table. And then this is just A minus mu over sigma, B minus mu over sigma, which agreed with this part here. It says that the probability, let me just repeat it, of A smaller than X smaller than B is just the probability that A minus mu over sigma smaller than the standard normal random variable, which is the one that we can get from the table, minus B minus mu over sigma. Let's do some examples. Let's suppose that x is a normal random variable with parameters mu equal 3 and sigma equal 3, standard deviation equal 3. And let's suppose that we want to compute the probability that x is between 2 and 5. Then what we do is we write 2 smaller than x smaller than 5. Then we subtract the mu, and then we have 2 minus 3 is smaller than x minus 3 is smaller than 5 minus 3, and we divide by the standard deviation, which is 3. And this is the, remember, x minus mu over sigma is the standard normal random variable, and that means that we want the standard normal random variable to be between negative 1/3 and 2/3. And then we want to compute this probability. This probability here is equal to the probability that C is between negative 1/3 and 2/3. But this is just the cumulative function evaluated at 2/3 minus the cumulative function evaluated at negative 1/3. 2/3 we can get from the table. We can do, this is C, we can round this. This is C of 2/3 is 0.67 minus, say approximately. And remember, when you have a negative number, you have to use this formula, which is due to the symmetry. C of a negative number, let's say minus C. If C is positive, then this is negative. It's just 1 minus C of C. Then this is just 1 minus the cumulative function evaluated at 0.33. And then this is the cumulative function at 0.67 plus the cumulative function at 0.33 minus 1. And this is the highlighted numbers show the probabilities that we need for this computation. 0.7486 plus 0.6293 minus 1, and this is 0.3779. Let's do another example. Let's suppose that with the same parameters, we want to compute the probability that x is bigger than 0. Then this is just x bigger than 0, and then we have to make the standard normal show up, and we do that by doing x minus 3 bigger than negative 3, and then when we divide by the standard deviation, we get that this is the probability. This is c bigger than negative 1, the standard. Then this is the probability that the standard normal random variable is bigger than negative 1, and we can see this as an integral from negative 1 to infinity, right? This is the interval, and here the density function dc, and this is just the cumulative function evaluated at infinity minus the cumulative function evaluated at negative 1. The cumulative function evaluated at infinity is the total area under the graph, which we know that is 1 minus, and when we want to compute the cumulative function at a negative number and we want to use the table, then we use the formula, which is this. This is just 1 minus the cumulative function at 1, and therefore we get that this is just the cumulative function evaluated at 1. The highlighted number shows the cumulative function at 1, and this number is equal to 0.8413. Another way to visualize this answer is the following. We want to compute the probability that c is bigger than negative 1. Here is negative 1, and here is the density function. Essentially, we want to compute this area, but because of the symmetry, to compute this area is the same as computing this area, which is the cumulative function evaluated at 1.